Kia ora team and welcome to another online tutorial. Today we're going to be talking about the 2017 Level 1 NCEA Mechanics exam, specifically question 3, working through A to D. Okay, let's get to it. So our question A, and as you can see in the very beautiful drawing that I provided, a crane shown above, fabulously, lifted a container 30 meters up in 15 seconds. They provided a weight force for the container at 60,000 newtons. Okay, they want us to, for AI, calculate the work done by the crane in lifting the container and calculate the power of the crane while lifting the container 30 meters in 15 seconds. Before we start these questions, I've just realized that I haven't provided the equations, so I'm just going to shop those in very quickly. All right, well, that's much better. Now we have the equations. The question asks us to calculate the work done. So we look down onto our equations, we look for work, and we see that work equals force times distance. Now, as always, and again, if you're in my class, you're probably used to or sick of me saying this, my first step is always going to be to write down the equation. So I'm going to equal work equals force times distance. Now I'm going to look at the equation and see if they've given me any information. They have. They've given me both the weight force at 60,000 newtons as well as the distance, 30 meters. Okay, and we're acting opposite the weight force, so we're doing that work. Okay, so equals 60,000 newtons times our distance, which is 30, 1,800,000 joules. Remembering that work done is the energy transformed during an action. Cool, let's get on to AII. Now for this question, they've asked us to calculate the power during this time. So again, my first step is to identify the equation. I come down the bottom and remembering that pressure equals force over area, so it's definitely not that one. The other P, power equals work over time. That sounds about right, so I'm going to get that equation in. Power equals work over time. We have our work from the previous calculation, okay, and they've provided us with the time. They've said 15 seconds because it took that long to lift it up. So we're going to calculate the power. Remember, the power is how much energy is used, or how fast, the rate at which energy is used or transformed is our power. Okay, so for us, it gives us 1,800,000 divided by 15 seconds, and we get 120,000 watts, W. Remember that watts are joules per second. So how much energy is being transformed per second? You could also give this answer as 120 kilowatts if you felt the need. Right? Kilo meaning 1,000 of. Now for B, they ask us, explain what work is being done on the container when it's hanging in the air without moving. Now, this may not seem relevant, but as always, what are we going to do first? We're going to write down the equation. Now, I've identified earlier the equation for work. We're going to stick to that. Okay, work equals force times distance. Now, we know the force, okay, 60,000, so I'm going to plug that in. Okay, and let's have a think about the distance. It's saying when it's hanging in the air without moving. So distance is 0. It's not moved a distance. It's stationary. Okay, so times 0. Now we know that any number times 0 is going to equal 0. Okay, so it has done no work. Okay. Stationary objects are not doing work. I would express this in a written form, but for the sake of us, we only have very limited space to do our working, and therefore I'm just going to keep it at no work, and I would expect you to write a much more comprehensive answer for this one, explaining as to why, focusing on no movement, therefore no work, and relating it back to our equation. So C asks us, or tells us, referring to the force diagram below, the one we see here, okay, explain the link between the vertical net force, acting on the container and the type of motion produced while the container is being lowered. Okay, In your answer, you should describe what is meant by net force and explain the link between the direction of vertical net force and the motion. Now, when they say you should, I'm going to say you are going to, because this is what you're going to be marked on, so make sure you do these things. Now, if we zoom in on our picture real quick, okay, we can see that the lower force is greater in size and magnitude than our upper force, okay? Now, I'm going to make a note. Force equals unbalanced, okay? Force is unbalanced. It's acting downwards. This being our net force, all right? And this force is in the direction of motion because it says they're lowering it down. So we've said that the force is unbalanced, so there's a net force acting. The net force is acting downward. They're lowering it, so this net force is acting in the direction of motion. So if we have an unbalanced net force acting in the direction of motion, we have acceleration. Okay? We know that if forces are balanced, it's either stationary or moving at a constant velocity, and that if net force is unbalanced and it's acting in direction of motion, okay, it's accelerating. If it's acting opposite, it's decelerating. So we know it's accelerating. Again, you would write out your answer in full, giving reasoning, linking back to these ideas, but we're very limited in space. So looking at D, we can see that the crane was lifting another container and the cable broke. The 650 kilogram container fell 15 meters to the ground below. The container had this much energy, 970,000 joules of kinetic energy, just before it hit the ground. Calculate the energy had before the cable broke. So we're going to do an EK equals EP equation, and explain why there is a difference in energy of the container when it was hanging from the crane compared to just before it hit the ground. Okay, so we're going to talk about efficiency here. But let's get into it. So as always, first step should be writing down the equation. So it says calculate the energy the container had before the cable broke. A container at height is going to have energy potential, specifically gravitation, so we're going to use our equation here. EP equals mass, gravity, height. Okay. Now I'm going to look. Gravity we have, mass we have, and height we have. So we're going to calculate that. 6,500 kilograms times acceleration due to gravity 10. That would be our weight force now. Okay. Times the distance, which is 15. And we get the potential energy, which is 975,000 joules. Okay. Now, we should already notice that this is a little bit different to the one they provided us. Okay. So, let's have a think about how much that difference is. So, we would go 975,000 minus 970,000 equals 5,000 joules difference. Okay. So something's not quite adding up here. They've told us that just before it hit the ground, it had this much energy. Okay. So there's a difference here of 5,000 joules, and we should state that. Now, let's talk about why. The main idea here is efficiency. Okay, what do we mean by this? We mean that not all of the energy has been transformed into, from potential into kinetic. Okay, when the object is held at a height, it is going to fall. Now, we would say in a perfect world with no friction, nothing happening, all energy would be transformed into energy kinetic. But we do live in a world of friction, okay? So I'm going to make a note of that. Okay, and due to friction, we have energy transformed into heat and sound. Okay, because energy is transformed into heat and sound, and we know how much, okay, due to friction as it moves through the air and rubs against those air particles, not all the EP is transferred into EK. Okay? So we can say that some of the energy that was stored at the top has been transformed into heat and sound due to friction. Therefore, there is slightly less energy. The object has slightly less energy kinetic by the time it hits the ground. Okay? Again, you would write this out in full sentences or paragraphs, but we are very limited with space, and I can't fit this all just in here. Okay? So, what have we talked about? For A, we calculated work. We also calculated power, right? For B, we talked about why an object that isn't moving or hasn't moved has done no work. Okay? For C, we talked about free body diagrams, forces being unbalanced or balanced, what that means if you have a net force in the direction against or with direction of motion, okay? And how that led to acceleration. Now for D, we've calculated the energy, we've talked about how it's different to what was observed and why that is. Efficiency. It's not an efficient system, it's not a perfect system. Friction exists, meaning that some energy is transformed into heat and sound, specifically for us 5,000 joules, meaning that by the time it hits the ground, it has a little bit less energy than when it was held up high. Okay? But that energy has not been destroyed, remembering that it cannot be created or destroyed, only transformed. It's been transformed, as we mentioned, into heat and sound. Hopefully that's been helpful, team. Hopefully it helps you to get out there and get into some physics or mechanics. Yeah. Good luck.